In the last lecture, we had started our discussion on unidirectional transport, that is where there is a variation in the concentration, temperature or velocity fields in only one direction. Recall that these fields are defined as continuously varying functions of position and time. When there is variation only in one direction and in time, we first derive a balance equation for a small differential volume. Take a balance of the change in mass in that differential volume, which is equal to the mass in minus the mass out plus any production. Okay. So, that is the basic conservation condition. Change in mass in a time delta t is equal to the mass in minus the mass out plus the production in the differential volume. The mass is the concentration times delta z times A. Mass in and mass out are due to the fluxes. These fluxes are only in the z direction because the concentration variation is only in the z direction. Okay. So, therefore, the fluxes are also only in the z direction. So, mass in and mass out are due to the fluxes in at z and z plus in at z and out at z plus delta z. Note that flux was defined as positive if it is in the plus z direction. The source term or the production term is basically the mass produced per unit volume per unit time by a reaction, for example. Mass produced if the substance is the product and mass consumed if it is the reactant. Okay. So, this is the production term, it is equal to this S, which is the mass produced per unit volume per unit time, times the volume and delta t. Note that the fluxes are multiplied by area and delta t and the production is multiplied by volume times delta t. So, we substitute all of these into the equations, divide throughout by volume A delta z, divide throughout by time to get a difference equation, okay, and then take the limit as delta z goes to 0 and delta t goes to 0 to get a differential equation. Okay. So, this is the form of the differential equation. And if I substitute, for example, Fick's law for diffusion for the flux. You recall that when we had done Fick's law, I had said that Jz is equal to minus d delta c by delta z, where delta c by delta z is the difference in c between two locations separated by a distance delta z. Okay. So, that was the difference form of Fick's law. In the limit as delta z goes to 0, this becomes minus d partial c by partial z. So, this is Fick's law of diffusion. Okay. And so, we had substituted the equation into Fick's law of diffusion, substituted the constitutive relation into the equation and we had got a conservation equation. And if the diffusivity is a constant, then it simplifies further. Okay. If the diffusivity is a constant, it is independent of position and so on, then you get an even simpler expression for the variation of the concentration with respect to position and time. This is a partial differential equation. It has derivatives with respect to z, second order derivative, and one first order derivative with respect to time, and it has the source term. So, this would require in general two boundary conditions in the z coordinate and one initial condition in time in order to be able to solve this equation. Okay. So, that is the mass conservation equation that we had seen in the previous lecture. Similarly, we had done the energy balance equation. This is actually done for the enthalpy within that differential volume. Okay. The change in enthalpy for a constant pressure process, I had written this as the enthalpy density H at z t plus delta t minus h at z t. Okay. Is equal to energy in minus energy out. Energy in due to the flux coming in at the location z, and energy out due to q z at z plus delta z. Okay. So, that is energy in at the location z, energy out at the location z plus delta z, the difference between those two, and then this is the source of energy. Okay. This S E is an energy produced per unit volume per unit time multiplied by volume multiplied by time. Okay. So, I get the balance equation. Okay. So, I get the balance equation, divide throughout by volume, divide throughout by time, to get a difference equation for the time t and t plus delta t, location z and z plus delta z. Okay. And take the limit. Okay. Delta t goes to 0, delta z goes to 0, the differences become partial derivatives. Okay. And then I had substituted for the enthalpy density. The time derivative of the enthalpy density is equal to the time derivative of rho Cp times T, okay, is equal to minus partial Qz by partial Z plus the source of energy. If rho Cp is a constant, okay, I told you that in most situations rho Cp is actually a constant. Okay. For example, for air between 0 and 100 degrees centigrade, it varies by only about 1%. In liquids like water, it varies much less by about 0.1%. So, then I can take rho Cp out and I get an equation which is exactly similar to the mass conservation equation, except temperature is substituted for concentration, thermal diffusivity for mass diffusivity, thermal energy source for mass energy source. And if the diffusivity is also a constant, then it simplifies even further. Next, let us look at momentum conservation. Okay. Okay. Turns out that the procedure for this is slightly different from what we had for mass and energy conservation, but in the end the result will be exactly the same, okay, for momentum transfer. Okay. Okay. In this case, we have volume, okay, z is equal to 0, z is equal to h, okay, and you could have two plates, for example, moving relative to each other, and this could result in some variation in the velocity. Okay. This could result in some variation in the velocity. Okay. How do we get the momentum conservation? Okay. First thing we note is that momentum is a vector. There is an x direction and there is a z direction. This velocity is the velocity in the x direction. Okay. So, there is a variation in the velocity in the x direction. The assumption is that there is no variation, I am sorry, there is a variation in Vx in the z direction. There is no variation in the velocity in the x direction. Okay. It is a unidirectional transport, which means that the velocity variation is only in the z direction. The velocity itself is in the x direction. The x velocity varies only in the z direction. Okay. And the conservation equation that we will write is for the x component of the momentum. Okay. There are three components of the momentum, x, y and z. In this particular case, the velocity of the boundaries is only in the x direction, and therefore, you would expect the velocity everywhere in the flow to also be in the x direction, provided the plates are parallel to each other. Okay, you would expect the velocity everywhere else to also be in the x direction, provided the plates are parallel to each other. Okay. So, for that I will take a small differential volume, okay, of height delta z, okay, and area A. Okay. I will expand that out once again. Okay. delta z, this is z, z plus delta z. Okay, set the now writing a momentum balance equation for the x momentum. Okay, so what are the forces acting on this in the x direction? Note that x is the direction of the velocity which is along the plates, and z is the direction perpendicular to the plates, which is the direction of momentum diffusion. In the x direction, in general, you will have pressure forces acting on the surfaces. Okay. The pressure always acts in the direction perpendicular to the surface. Okay. The pressure always acts in the direction perpendicular to the surface. Therefore, the pressure force will act on the surfaces perpendicular to the x direction. That is one contribution to the force acting on the surface. Okay. And then you will have shear stresses acting on the surface. Okay. So, you have on the top surface you will have a shear stress, okay, tau x z, and this has a unit normal n. Okay. On the bottom surface the unit normal is in the minus n direction. Okay. Okay. Tau x z defined as the force per unit area in the x direction acting at a surface whose outward unit normal is in the z direction. At the top surface the outward unit normal is in the z direction. Therefore, the force acting in the x direction is tau x z. Okay. At the bottom surface the force the outward normal is in the minus z direction. Therefore, the force acting in the minus x direction is going to be tau x z. Okay. Note that if I have on a surface, right. So, if I have the force tau x z exerted on the volume below, okay, exerted on the volume below, then this volume will exert an equivalent opposite force on the volume above from Newton's third law. Okay. So, if tau x z is the force exerted on a volume with outward unit normal in the plus z direction, okay, for the volume below the outward unit normal is in the minus z direction. Okay. And the forces have to be equal and opposite. That means that for the volume below the force is being exerted in the minus z direction. Okay. Therefore, tau x z is the force per unit area exerted on this surface, okay, with outward unit normal in the z direction. If the outward unit normal is in the minus z direction, the force is exerted in the opposite direction. Okay. So, those are the stresses exerted on the surface. Okay. Momentum conservation condition is slightly different. It comes from Newton's laws. Okay. The condition is that rate of change of momentum is equal to sum of forces. Rate of change of momentum is equal to sum of forces. Okay. So, let us examine this one by one. Okay. So, rate of change of momentum in time delta t is equal to the momentum at time t plus delta t minus the momentum at time t divided by delta t. Momentum we are talking about is the momentum in the x direction. Okay. So, is equal to rho v x at z t plus delta t minus rho v x at z t. This is the momentum density. I have to multiply it by the volume, which is a delta z divided by delta t. That is the rate of change of momentum. Okay, that is the rate of change of momentum. Okay. So, the rate of change of momentum consists of two parts. One is momentum in minus momentum out plus the sum of forces. Okay. Now, there is momentum coming in and out of this differential volume. So, let me draw it once again here. Okay. In this particular case, there is fluid velocity. Okay. So, there could be convection as well. Okay. There could be convection as well, momentum coming in and going out due to the fluid velocity. Okay. The fluid velocity is in the x direction, the velocity varies in the z direction. Okay. So, there could be momentum coming in on the left side and momentum going out on the right side, because there is fluid that is coming in on the left side, fluid that is going out on the right side, and it is carrying the momentum along with it. In this particular case, we are considering unidirectional flow, unidirectional transport, where the velocity is in the x direction, but the velocity variation is only in the z direction. Okay. Therefore, the velocity on the face on the left and the velocity on the face on the right are the same. The velocity variation is only perpendicular, is only in the direction, in the z direction, okay, which is the vertical direction in this case. So, there is a momentum coming in on the left, a momentum leaving on the right. Since the velocity is equal on both faces, the net momentum coming in and going out due to convection is exactly the same. Okay. So, in this particular situation, even though there is velocity, there is flow, because it is unidirectional, there is no variation in velocity in the x direction. The momentum coming in and the momentum going out on the left and right faces is exactly the same. And because of that, there is no net change in momentum due to the fluid coming in and going out. Okay. So, these terms, momentum in and momentum out, can sum to 0. Okay. These terms sum to 0, and you only have the sum of forces that are exerted. What are the sum of forces? Okay. One is a pressure force. Pressure on the left side, pressure on the right side, acts perpendicular to the surface and therefore in the x direction. Pressure is always compressive, it always acts along the inward unit normal. Okay. If the flow is unidirectional, there is no variation in the x direction, right. If the flow is unidirectional and there is no variation in the x direction, then the pressure on the left side will be exactly equal to the pressure on the right side. The two act in opposite directions, and the sum of forces due to this pressure is equal to 0. Okay. So, therefore, this pressure term can also be neglected in this balance. Okay. I should note that this is specific to unidirectional flow in which there is no pressure gradient. Okay. If there were a pressure gradient, then this pressure on the left and the right sides would not be equal. That we will examine separately when we look at pressure driven flows. In this case, for this particular conservation equation, I will assume that there is no pressure variation in the x direction. So, the pressure on the left face and the pressure on the right face will be equal, surface areas are equal, and therefore, the force is also equal, and these two cancel out. What we are left with is the forces that are exerted on the top and bottom due to the shear stress. So, what is the sum of forces? Okay. I said that the momentum in and the momentum out on the right and left are equal. So, they sum to 0. the pressure on the left and right are equal. We are not considering pressure variations. Therefore, the sum of forces is just due to the stresses exerted on the top and bottom face. The force on the top face is going to be equal to tau x z at z plus delta z times the area A. Okay. Tau x z at z plus delta z times the area A. Okay. And the force at the bottom is in the minus x direction, because the unit normal is in the minus z direction. The outward unit normal at the bottom is in the minus z direction. So, the force is in the minus x direction, minus tau x z at z times A. Okay. These are the surface forces that are exerted at the surface at z and the surface at z plus delta z due to the shear stress. Okay. Recall that shear stress acts tangential to a surface. Okay. So, this is the sum of forces. Okay. This is the sum of the surface forces. Okay. So, let me just qualify that and write this as this is the sum of the surface forces. In addition to this, there could also be what are called body force. Gravitational force is, for example, an example of body force. Okay. The body force is the body force density is defined as the body force per unit volume per unit time. Okay. So, you know that if I have a volume of fluid, okay, of mass m is equal to rho times delta v. Okay. The volume is delta v, the mass is rho times delta v, then the gravitational force is equal to rho delta v into g. This force is proportional to the volume delta v. Okay. So, the gravitational force density is equal to rho g. Okay. In general, you could have gravitational forces, centrifugal forces and other such forces. All of these forces are proportional to the volume. Okay. So, therefore, this second contribution, sum of body forces, this is in the x direction in this particular case, will be generally of the form f x times delta v. Okay, it will generally be of the form f x times delta v is equal to f x delta a delta z. Okay, so, that is going to be the body force density, okay, the sum of the body forces. So, here we have the rate of change of momentum, surface forces and body forces, and we need to add up all of them. Okay. Okay. Into A is equal to tau x z at z plus delta z into A plus f x A delta z. Okay. So, in this particular case, we divide throughout by A delta z, okay, divide throughout by A delta z, and rho V x at plus f x. Okay, I divide throughout by the volume A times delta z in this case. Take the limit delta t delta z going to 0, partial of rho v x. Okay. When I write this, I am permitting the possibility that rho could also be a function of time and position, is equal to partial tau x z by partial z plus f x. Okay. That is the momentum balance equation, where f x is the body force density, tau x z is the shear stress. Okay. Newton's law. Okay. Tau x z is equal to mu partial v x by partial z. Okay. Note that Newton's law does not have a negative sign in it, okay, because we defined the stress as positive if it acts as a surface whose outward unit normal is in the plus z direction and thereby increases the momentum of the volume below, whereas heat and mass were defined as positive if they are in the plus z direction and increase the energy or mass of the volume above. Okay. So, because of that difference. Okay. So, therefore, the equation becomes partial rho v x plus okay. If density is a constant, as it is for incompressible fluids, if density is a constant as it is for incompressible fluids, then I can take rho outside and I will get rho times partial V x by partial t. I can divide throughout by density if it is a constant. You can divide throughout by density if the density is a constant. And mu by rho is the kinematic viscosity, nu, or momentum diffusivity. If momentum diffusivity is also a constant, then the equation becomes partial V x by partial t. Okay, so, these are the equations. And once again you see that these are exactly the same as the concentration equations that I had, partial C by partial T is equal to plus S So, the mass, momentum and energy conservation equations have the exact same form when they are expressed in terms of the diffusivities. Okay. If the diffusivity is not a constant, then you have this particular form of the conservation equation. Okay. If diffusivity is a constant, you can remove it, take it out of the derivative, okay, and you get this particular form of the conservation equation. So, these conservation equations, mass, momentum and energy, have the same form. They are both first order in time, second order in the z coordinate for unidirectional transport. Okay. To get the equation for momentum, you just substitute velocity for concentration, momentum diffusivity for mass diffusivity, and the body force by density for the source. Okay. They are both first order, and the second order in space requiring two boundary conditions, first order in time requiring one boundary condition, therefore, we can get general solutions, okay, without reference to the specific transport that is taking place. We can get a solution, and in that if we solve a mass transfer problem, for example, and in that same solution we substitute temperature for concentration and thermal diffusivity for mass diffusivity, you will get the solution for a heat transfer problem. So, at the microscopic scale they are exactly the same, with the important caveat that momentum conservation, this form of the equation is valid only when there are no pressure variations. If there are pressure variations, then that also has to be included. So, this is restricted to unidirectional flows in which there is no pressure variation. Apart from that, the three are exactly the same. So, this completes our derivation of conservation equations for unidirectional flow in this Cartesian coordinate system. I will continue with some applications in the next lecture. I will see you then.